All right, now as we enter into example 3, let's learn about just kind of some rules here. It says here independence of a limit from a function value at a point. And what this is trying to show you is that given all three situations here, where you have a graph, kind of like the last problem we saw, example 2, where you have something that's undefined at that spot, as long as the graph from both sides, both the left side of the graph and the right side, is approaching this point, L will be the answer to the limit at the value c. As the limit of this function as it approaches the x value of c, the limit would be the value L. And now on this second situation, it's showing you the same thing, but we have the graph itself actually defined way up here at the value n. Well, the limit would still be the value L. Even though the function itself exists at n, the limit would be L because that's where the graph was approaching, both from the left side and from the right side. The graph was approaching this point here. Even though the function itself does not exist there, it exists up here. The limit here would be L, even though the function value would be n. And here, this function would be undefined. So if you're wondering why is that G, why is that F, they just called this equation F here and this one G. All right, now let's look at equation H. So now you have a function and it's defined at all points. Well, as you approach this value c, you can still see it's approaching this value L. So again, the limit would be L. So it doesn't really matter what the one point is when you look at limits. What you're doing is evaluating where the function is approaching and where is it going from both the left side and the right side. So with that, we have different names. We call the left-hand limit, and it'll be represented by this as x approaches c with a little negative. That would be the left side, and if it were a plus, that would be the right side. Again, all this is reviewed from lesson 1-3. If we have a left-sided limit that equals the right-sided limit, we have a limit at that spot for the function. This is only true if the left hand equals the right. If the left does not equal the right, then we do not have a limit of that function at that point, which we'll see as we go along. So here's part A. Given this graph, which is this equation f of x, we want to estimate the left-hand limit, the right-hand limit, and if we can, determine the entire limit. So on this graph, as we're looking at the value 1, as this graph approaches the value 1, what we can notice is the y values here. From the left side, it's approaching this y value right here, which they haven't labeled this, we'll label it a -2. Which means the limit of f of x as x approaches -2 from the left side, the y value it's approaching would be -2. That would be the left-hand limit. That's the left-hand limit. Now on the right side, I'll do this in red, on the right side the graph is approaching 1 this way to this point here, which this would be 1, 2, and we'll call that 3. Okay, so as from the from the right side, as x approaches -2 from the right side, that's what that plus right there means, the limit would be 3. This would be known as the right-hand limit. Right-hand limit. Now, because the limit of f of x as x approaches -2 from the left does not equal the limit, the limit of f of x as x approaches the -2 from the right side of the graph, since they were not equal to each other. Because of that, let me write since. It doesn't look like since, it looks like sine. Here we go, let's try this one more time. Since the limit of the left side does not equal the right side, the overall limit does not exist. Limit of f of x as x approaches, I just realized I was writing a -2, I need to change that to positive ones, does not exist. And so now let me go back here. I wrote all these -2s. I should have been writing -1s. I apologize for this. Let me replace all of those. Okay. Now they got that. We're talking about as x approaches 1 from the left side, 1 from the right side. 1 from the right side and 1 from the left side. That's how I should have wrote it. Because these do not approach the same point, the overall limit at 1 does not exist, but the left hand does. The left hand's value, the left hand limit is -2. The right hand limit is 3, but the limit as x approaches 1 from both sides would not exist. All right, here's part B. So looking at this graph, as we close in on 0, that's what we're looking at. The left hand limit would exist. We're approaching a point. Specifically, we're approaching the point -1. So from the left side, they call this function g of x. As x approaches 0, the y value that we're approaching is -1. This would be our left-hand limit. I'm going to abbreviate here, left-hand limit. Okay, now from the right side, it's approaching the same spot. So limit of g of x would also equal -1 as x approaches 0 from the right side. Ooh, I forgot to write the left side over there. Okay, this would be called the right-hand limit. Right-hand limit. Now, since the limit of g of x as x approached 0 from the left side equal the limit as g of x limit of g of x as x approaches 0 from the right side. Since that is true, what does that mean? That means the limit of, not f of x, g of x as x approaches 0 would equal -1. That's because these two are equal. And I just realized I haven't shown you how, this is called Piecewise, and it's been a long time since I've shown you how to graph that. If you go to your pre-programmed graphs, you could open up Piecewise there, and that's how you could graph this function. So you would just type in the branches as we go. This is 2 branches, so in step 1, I'd put the first branch here, x squared minus 1, as long as x is less than 0. Let me put this as x is less than 0. And for branch 2, we would have 1/4 x minus 1 if x was greater than or equal to 0. Greater than, equal to 0. And so that's how you can get the same picture on Desmos. Now, here is one for you to try.